So I'm Shalvi Mahajan, working as data scientist at SAP SC, Germany, currently located at Munich. Previously, I basically worked at Allianz as data scientist and at Samsung R&D as software engineer. And at SAP, we are working on building and validating various ML use cases so that they can be adopted in various products across different industries. And today's topic that I'm going to deliver is natural language understanding and inference, which are actually the sub parts of NLP. So today's agenda would be a little bit on the topic background, so that if someone does not know the topic in detail, they can also know what NLP actually is. NLP approaches from basic to advanced, some of the representation methods, transformation methods, natural language understanding, which actually is the topic, and a conversation, how it is useful in conversational AI, machine translation, natural language inference, and finally the conclusion. So to start with, everyone knows what natural language is. It's the method of communication which could be either speech or text. NLP provides an automatic computational processing of human language. So basically, it combines the computational linguistics, rule-based modeling of human language with statistical, machine learning, and deep learning models. So some of the few tasks that NLP actually does is speech recognition. POS tagging is part of speech tagging, which is a grammatical tagging in a text. Named entity recognition is like whether in a sentence this is a time or location or what entity it belongs to. Then co-reference resolution. So co-reference resolution is like if I say Shalvi is going to market, she will be late. So she here refers to Shalvi. That is a co-reference resolution. So that NLP model should be capable of doing. Machine translation. So machine translation, everyone knows, and everyone is familiar about Google Translate, DeepL, and so on. Sentiment analysis, which actually tells from a text or a speech what sentiment a person wants to indicate or what intent does he have. Next comes the NLP approaches from basic to advanced. So initially we had rule-based NLP, which is regular expressions, something based on just rules. Text normalization is quite common in NLP, which is word tokenization, lemmatization stemming. So what exactly is word tokenization? It's, for example, if you have a long sentence, you just have removed the stop words like is, are, and you just have the useful words in your sentence so that we know the meaning of the sentence. Lemmatization is like having a basic verb. For example, if I say she's doing better, so better belongs to good. So good is a lemma of better. So that's lemmatization. Stemming is like I say she's walking. So walking, I remove ing from walking, and walk is the stem. So that's the stemming. So basically, we just normalize the whole sentence or the text. Minimum edit distance is just written so that we can compare the two sentences, how close they are by calculating the edit distance in between them. If that's the problem that we have to solve, which is calculated using Levenshtein distance. We can also talk about this distance in a bit more detail, but I think for now, let's just keep it like this. So if you in case have any questions, feel free to just ask in the chat or Q&A. Next comes the statistical or stochastic NLP. So it is an optimization problem which aims to maximize the probability of the output given the input, like what we do in Bayesian approach. Then is the vector method. So I'll explain the vector methods in detail in the upcoming slides. So it's basically some bag of words, n-gram approach, some of the embedding methods, word-to-vec TF-IDF, which I'll explain. Deep learning and neural network methods are also there, like recurrent neural networks and LSTM. So for now, this it's not important to touch these topics, I think. So yeah, just a second. Yeah. So the representation methods are, the bag of words is one of the representation methods. So what does it mean by representation method is like, for example, if you have a corpus or a document with lots of text, how would you represent each and every word? So one of the method is bag of words, which actually, for example, in this case, it's, let's say we have a lots of documents with lots of vocabulary in each of them. So each row will represent a single observation. And the cell here represents the count of the word represented by the column in that observation. So for example, in the document 0001, we had biolog 12 times appeared. And that's how we measure for each and every word after removing the stop words, lemmatization, doing the stemming, and so on. So basically, this article class, for example, here is a label. Let's say if we are to do some kind of a classification or a supervised problem, so that label would help in this case. So this is one way of representing our text. The second way is embedding metrics. So embeddings can be made for each of the words present in the vocabulary. And so what exactly is embedding is to represent a word in a high dimensional space. That's embedding. And this can also be represented in the form of matrix. So the transformation methods are what I talked about the embeddings. So a few of them are mentioned here in this slide, just so that you can go with my topics in the next slide. So for example, what we do is words in the text are mapped to vectors of numbers. So for example, we have TF IDF, so it's the term frequency inverse document frequency. So that's the formula. So what it does is basically counts the number of how many times does the term appeared in that document. And also the inverse document frequency is represented with this formula, logarithmic of n, which is the total number of documents divided by the number of documents containing that term. So that's inverse document frequency. On the right, you can see how word vectors look like. So basically, like a king will be represented somewhere like here. Man would be represented here, queen here, and women here. So that shows that how different king and queen is from each other based on when we map them on a high dimensional space. One-hot encoding is nothing but what I explained on the bag of words. It would just take whether the word is present or not. That's all. So if it's present, it will mark it 1 or 0. So it's a kind of a binary encoding, let's say. So word embedding methods other than that are like word2vec, fast-vec. So they also do the similar things as bag of words, similar to that. So this is just to explain the difference between character bag of words and scriptgram, but it's not that relevant for this slide. But other than that, since computing such embeddings takes a lot of time and is very expensive, so doing that every time for every vocabulary and every corpus, it's difficult. So it's better to use the transfer learning, where the model is trained on one task and is repurposed on a second related task. It can be reused and tested on the second related task. So by this, we can just avoid training it again and again. So now comes the main gist of this session, which is natural language understanding. So natural language understanding is also one subset of natural language processing, which uses syntactic and semantic analysis of text and speech to determine the meaning of sentence. So basically, NLP is constituting of natural language understanding and natural language generation. So natural language understanding is actually the core of NLP. How it's that it covers the reading aspect of NLP. So what NLP does is turning the text into structured data, while what NLU does, it covers the reading aspect, the intent of the text. So I think it's the core component of NLP. For example, entity detection to know what the sentence, what the words in the sentence implies to, like if it's a place, it's a location, what entity it is, or a topic classification, like whether this email is a spam or not. So, and also NLU is a very, very important part in conversational AI. We'll see that in a second. And natural language generation is just that, the structured data that you got in during processing to convert it into an output text. So natural language Understanding basically establishes relevant ontology or data structure which specifies the relationship between words and phrases so that we know the meaning. For example, we have these two sentences. A human can know the difference between the same word used in the two sentences. For example, Alice is swimming against the current, and the current version of report is in the folder. So in the first sentence, current is a noun, but in the second sentence, it is used as an adjective. So human can make the difference. And in case of NLP, NLU basically focuses on this reading comprehension through grammar and context and enables to determine the intended meaning of the sentence. And that's actually very, very useful part in an NLP model. So for conversational AI, it refers to the technologies. Everyone is familiar about the chatbots, voice assistants, which users can talk to. For example, Apple Siri, Alexa, Google Assistant, etc. So how does NLU actually help here? So the main parts of a chatbot or a voice assistant is intent classification and entity extraction. And as I discussed above in my previous slide, they are also the primary drivers of conversational AI. So intent classification is nothing but just knowing the intent of a sentence. So for example, an NLU model is fed with the label data with a list of known intents and example sentences that correspond to these intents. And once we train this model, the model should be able to classify a new sentence that sees what intent it should be defined onto. So it's a supervised learning example. And entity extraction is, again, the same thing to recognize the key pieces of information in a given text, time, place, name of a person, just to get an idea and a feeling of additional context and information related to an intent. And why is it like important in conversational AI? So it's important as, for example, if you see here in this example, a person says, I want to go on a vacation. The chatbot says, fun, let's do it. Who's going? So this part, fun, let's do it, who's going, tells that it's something related to vacation, and that chatbot is able to know. So it's an intent that a good chatbot should be able to get a feeling of. And the second is just, and then the person says just me, and the chatbot says perfect, where do you like to go? So this is the second part is basically an entity instruction, where. So where is a good chatbot should know that it's talking about, it should next talk about the location. So based on the input from your NLU model, the current state of conversation and its trained model, the core component should be of a chatbot should be able to decide the next course of action, which could be sending a reply back to the user or taking any action like suggesting something and so on. So one of the good examples right now is the chatbot Meena, which is actually the chatbot from Google. And it's an end-to-end neural conversational model that learns to respond sensibly to a given conversational context. And by sensibly, what I mean, I'll discuss in the next slide. And the training objective is just to minimize perplexity, which is to maximize the probability and on an unseen test set. So basically, perplexity is just average branching factor in predicting the next word. And this is just an overview of the architecture that it has, a transformer, sequence-to-sequence architecture, where it has one evolved transformer encoder block and 13 evolved transformer decoder blocks. The transformer is also a sequence-to-sequence architecture with overall transformer has encoders, which encodes the input into embeddings, and decoder to decode the embeddings to output. By evolved, it just has additional convolutional neural network layers on the entry and the exit points. So that's a bit of a more detail, but here the metric used to measure the performance of Meena was basically sensibleness and specificity average. And how did it come? So for example, a person says, I love tennis, and the chatbot says, that's nice. So it makes sense, yes. Definitely sensibleness is good, but it is not specific. It is not specific in the context. It's like to say it for any other comment. It's just any other comment. But a good chatbot should say, me too, I can't get enough of Roger Federer, which is very, very specific. So so this plot on the left side basically compares humans and different variety of chatbots, including Nina. So these chatbots are also open source. So the sensibleness of a chatbot is the fraction of responses labeled as sensible, whether it makes sense, the reply makes sense or not. And the specificity is the fraction of responses that are marked specific. And the average of these two is this SSA score. And Nina actually performs quite well. It actually beats the state of the art currently. So before going into the natural language inference, I just wanted to clarify a bit more on machine translation because these topics are a bit related. So machine translation is just converting one language to other, preserving the original meaning of the input and producing fluent text in the desired language. For example, Google Translate, everyone uses. And so some of the types of machine learning translation is statistical models, which actually deal with huge volumes of bilingual content. It's very simple, something which Google Translate also use, just translating a corresponding word from a source language to the objective language. Rule-based machine translation is just using with the help of a regular expressions. So the example shown down below, where the input sequence is as high, converting to is it hot, it is using a statistical model doing it word by word. And hybrid version would be the mix of rule-based and a statistical one. And based on a neural network, it's also just using a statistical model, but training it with the help of a neural network model. So the second part of this session is natural language inference. So natural language inference is just studying whether a hypothesis can be inferred from a premise when both are text sequences. So as you can see on the right, there are different languages being written, and on a high dimensional space, if we map one sentence with the other, we should know how close these two are, irrespective of the language. So it should be able to determine the logical relationship between a pair of text sequences. So such a relationship usually fall into three types. Entailment. Entailment is, yes, the hypothesis can be inferred from the premise. Contradiction is the negation of the hypothesis that can be inferred from the premise, and neutral is like any other case where it doesn't matter. Yeah. So now how do we actually do natural language inference? So one of the idea is using attention mechanism. So what it does is, if we look on the left side, so if the premise is I do need sleep and hypothesis is I'm tired, so first step would be to use the alignment or the attention, which is the weighted average between the words in one text sequence to the words in the other text sequence, and just seeing like if I is well aligned with I and sleep is well aligned with tired, but not the rest of the words. So that's the first step. Then we have a set of word and the aligned words. So we can do this comparison, and how does it work is it basically concatenates the word from one sequence and aligned ones from other sequence into a function. So it just concatenates these words. Then comes the aggregation. Aggregation is, as the word suggests, summing the output from these embeddings, because these are all definitely embeddings, and then concatenating them, and finally predicting them. So just a follow-up demo of what I did basically on a Stanford natural language inference dataset. So here it's just a summary of how it would look like. So as you can see in the forward pass, we have this premise and hypothesis. We create the embeddings out of them. Then we use attention, attend function, comparison, aggregation, and here on the right side, we can see how the train loss looks like. So train loss is decreasing, and it found its global minima somewhere after epoch 3. So here, finally we predict, we create this function and predict, and based on the label, either it's 0, 1, we say what, is it an entailment, contradiction, or if it's none of these. So finally, if I wrote he's good after training on a vocabulary and he's bad, so it's a contradiction, it knows. So basically, natural language inference helps in mapping sentences from multiple languages that can be processed using language agnostic multilingual models. So here in this example, it was just English, but we can do it for multiple languages. And it can analyze how closely they are related to each other in a high dimensional space. So finally, the language agnostic, a little bit on language agnostic model. So Facebook has made one of the library called Laser, where it is doing the same thing. It maps a sentence in any language to point in a high dimensional space with the goal that the same statement in any language should end up in the same neighborhood as we've seen. So this representation could be seen as a universal language in a semantic vector space, and it also has lots and lots of languages, and its accuracy is quite well. And we have observed that in this library, the distance in that space correlates very well to the semantic closeness of the sentence. And this is one of the example library of how to use natural language inference. So finally, words in the text are what we actually did in this presentation. So words in the text can be converted into vector and embedding forms to process the language in a model, and natural language inference, understanding and generation, both are the subtopics of NLP, which constitutes NLP, and has a major, the NLU at least has a major contribution towards conversational AI. It's a core component, and language agnostic models map sentences from different languages in high dimensional space to see their semantic closeness. And in NLI, the attention model, this consists of actually 3 steps to determine the logical relationships between premises and hypotheses is attending, comparing, and aggregating. So that's all. So I'll now look into the questions. I hope my slide was able to convey the message. Okay, that's fine. I've seen some examples of Google translated sentence from a gender neutral pronouns to another language that uses he, she, and it would assume she is cooking, he is a doctor. Is that problem with the training data, and could it be fixed with clearing other pairs in sentences? So yeah, that's basically a problem, because currently most of our data set is biased and is trained on a biased data set. That's why it creates a problem. And that is something which everyone is now focusing on, to remove this gender biasing from the training data set on the corpuses. So yeah, and soon hopefully we'll see. So Google is also working on this Google Translate component, so that the biasing shouldn't be there. I don't see any more questions, although good comments. Thanks a lot, everyone. What would you recommend to entry levels? So NLU, I wouldn't say is entirely just a separate field. It's a part of NLP. So if you want to start basically with NLP, you can maybe look into some Coursera courses, or some on YouTube. Maybe you can find some Stanford related courses as well. And feel free to contact me. We can have a discussion, a long discussion on it. I'm on LinkedIn, and I'm happy to take questions there as well. Yeah. So skills, I think Python should be good enough. But other than that, it's more of a conceptual thing, and the basics of machine learning would help. So yeah, again, Coursera or Stanford videos would be good. Any other questions? So if there are no other questions, so feel free to contact me on LinkedIn. I'm happy to take any other questions personally as well. Thanks a lot, everyone, for your attention, and stay safe and take care. Thanks.